Have you ever pondered why grammatical format matters in the theory of automata? Well, it's a key element that aids in defining the syntax of formal languages and generating valid strings. Think of it as the blueprint for constructing a language. In the realm of automata and formal languages, grammatical formats come in several types, each with their own rules and structures. From the simplest form, regular grammars, to the more complex, such as context-sensitive and unrestricted grammars, each type offers a unique set of tools to structure a language. Choosing the right grammatical format depends on the intricacy and structure of the language being described. Simpler languages might only require a regular or context-free grammar, while more complex ones could necessitate a context-sensitive or unrestricted grammar. So, understanding grammatical format is essential to comprehend the structure and rules of a formal grammar. Diving into the first type, we encounter regular grammars. Regular grammars are the most elementary form of grammatical formats in the theory of automata. They serve as the foundation for understanding more complex grammars. So let's take a closer look. At the heart of regular grammars are production rules. These rules are straightforward and can be represented in two forms: A, AB, or A, alpha. A and B in these rules are what we call non-terminal symbols, while alpha is a string composed of terminals and occasionally non-terminals. Now, you might be wondering, what's the deal with these terminals and non-terminals? Well, in the realm of formal languages, terminals are the basic symbols from which strings are composed. Non-terminals, on the other hand, are symbols that we can replace with combinations of terminals and other non-terminals, following the production rules. So how do we use these rules? It's quite simple. We start with a non-terminal symbol, and we apply the production rules to gradually replace non-terminals with terminals, until we end up with a string composed entirely of terminals. The set of all strings that we can produce in this way forms what we call a regular language. Now let's talk about the connection between regular grammars and regular languages. Regular languages are in essence the languages that can be generated by applying the production rules of regular grammars. They hold a significant place in the world of formal languages and automata theory because they can be recognized by finite automata. This means that there's a direct correlation between the structure of a regular grammar and the structure of a finite automaton that recognizes the corresponding regular language. And there you have it. The simplicity and elegance of regular grammars make them a powerful tool in the world of automata and formal languages. They might seem basic compared to other types of grammars, but don't be fooled. Regular grammars, though simple, play a crucial role in generating regular languages. Moving on to the next type, we have context-free grammars. These grammars are a step up in complexity from regular grammars. They're known for their association with context-free languages, and they bring a greater degree of power to the table. So what makes context-free grammars stand out? Well, their structure and rules are slightly different. Each production rule in a context-free grammar follows the format A, beta. Here, A represents a single non-terminal symbol, and beta is a string that can be comprised of both terminal and non-terminal symbols. This format allows for more intricate combinations and possibilities in string generation. But where do we see context-free grammars in action? They're widely used in defining the syntax of programming languages. If you've ever written a line of code, then you've interacted with a language shaped by a context-free grammar. These grammars provide the rules that determine how you can construct valid statements in that language. They set the structure for how commands, variables, and expressions interact. In addition to programming languages, context-free grammars also find their way into document structuring. For instance, they're used in defining the rules for structuring HTML and XML documents. These grammars ensure that these documents are well-formed and adhere to the correct nesting and hierarchy of tags. Lastly, context-free grammars play a significant role in modeling the syntax of natural languages. They help linguists and language researchers to build models that can capture the complex rules of sentence formation in human languages. Think of them as the architects behind the structure of the sentences we speak and write every day. So, in essence, context-free grammars are incredibly versatile. They provide the rules for everything from the code that builds our digital world to the structure of web documents and even the way we construct sentences. Context-free grammars, with their wider applications, help in defining the syntax of programming languages and more. Next in line, we have context-sensitive grammars. These grammars are a step up from context-free grammars in terms of complexity and power, They are associated with the class of context-sensitive languages. Now, what sets context-sensitive grammars apart from other types of grammars? It's the allowance of context-sensitive conditions in their production rules. When we talk about context-sensitive conditions, we mean that when a non-terminal symbol is replaced, it's not just the symbol itself that matters. The surrounding context also comes into play. This means that the string of symbols before and after the current non-terminal symbol can influence how it's replaced. Let's take an example to illustrate. A production rule in a context-sensitive grammar may look like this: AB, BA. Here, the non-terminal symbol A can be replaced by B, but only when it's followed by B. This is what we mean by context-sensitive conditions. This ability to consider context brings a whole new level of power and complexity to context-sensitive grammars. They are capable of generating languages that are beyond the reach of context-free grammars. Now, where are context-sensitive grammars used? They are primarily used in modeling complex language phenomena, particularly in natural language syntax. For example, in English, the agreement between the subject and the verb in a sentence is context-sensitive. A singular subject requires a singular verb, and a plural subject requires a plural verb. This is a context-sensitive rule, and context-sensitive grammars can effectively model such rules. However, this added power and complexity also means that context-sensitive grammars are more challenging to work with. They require more computational resources to process and generate strings, and their rules can be more difficult to construct and understand. In summary, context-sensitive grammars, though more complex and demanding, offer a detailed perspective on language syntax. They allow us to model and generate complex language phenomena that are beyond the reach of simpler grammars. Context-sensitive grammars, though complex, offer a detailed perspective on language syntax. Finally, we touch upon unrestricted grammars. These grammars, also known as Type 0 grammars, are the most powerful and flexible in the hierarchy of formal grammars. Unlike the other grammars we've talked about, unrestricted grammars have no restrictions on the form of production rules. This means that they can consist of rules of the form alpha, beta, where alpha and beta are strings of terminals and/or non-terminals, and alpha is not empty. This freedom allows unrestricted grammars to generate a broader range of languages than any other type of grammar. They are associated with recursively enumerable languages, which are the most general class of formal languages. Recursively enumerable languages include all languages that can be generated by an algorithmic process, plus some that cannot, such as the halting problem language. The halting problem language consists of descriptions of computations that halt, a problem that has been proven to be undecidable. However, this power and flexibility come at a cost. Unrestricted grammars can be challenging to work with due to their complexity. They can generate languages that are so complex that no algorithmic process can recognize them. This means that in practice, it can be extremely difficult, if not impossible, to determine whether a given string is in the language generated by an unrestricted grammar. Furthermore, because unrestricted grammars can generate languages that are not decidable, they can't be used for practical applications like defining the syntax of programming languages or modeling natural language syntax, tasks that are better suited to less powerful but more manageable grammars like context-free grammars. Yet, despite these challenges, unrestricted grammars play a crucial role in the theory of formal languages and automata. They provide a theoretical upper limit to what formal grammars can achieve, and they help us understand the limitations of algorithmic processes. Unrestricted grammars, despite their complexity, can generate languages that extend beyond the capabilities of other grammars. So these were the 4 types of formal grammars used in the theory of automata. We kicked off with regular grammars, the simplest type, closely associated with regular languages and recognized by finite automata. Then, we moved on to context-free grammars, offering more power and widely used for defining programming languages, structuring documents, and modeling natural language syntax. Our exploration continued with context-sensitive grammars, even more potent and used for modeling intricate language phenomena, their production rules influenced by the surrounding context. Finally, we dived into the unrestricted grammars, the most unrestricted type, associated with recursively enumerable languages, capable of generating languages beyond algorithmic recognition. Each of these grammatical formats, from the simplest regular grammars to the unrestricted ones, has its unique place in defining the syntax of languages and generating valid strings. Remember, the choice of grammatical format depends on the complexity and structure of the language being described. Each grammar type gives us a unique lens to view and understand languages.